There are no radioactive materials in this room with me. There is no particle accelerators, there is no atom bomb that had exploded. Yet, every few seconds, a bright white streak appears out of nowhere, crosses the chamber, and disappears forever. What you're seeing now is something called a cloud chamber. Inside the cloud chamber is a layer of alcohol vapor that's been cooled from below until it's supersaturated. Supersaturated meaning that there is more vapor present in the chamber than there should be. These vapors are cooled to below their condensing point, yet they don't condense because they need to actually have something to condense around, something called a nucleation point. When a charged particle flies through the chamber, it tears electrons off the molecules in the chamber, creating ions. Those ions become nucleation points. The alcohol immediately condenses around them. For a fraction of a second, the invisible path of the particle becomes visible as a thin white trail of condensed alcohol vapors. The thick and bright pencil-like tracks are caused by alpha particles. The alpha particles are the nuclei of helium atoms. The thin, squiggly tracks are caused by beta particles, which are electrons that are moving at really high speeds. So the cloud chamber serves as a reminder as to how we are always constantly bombarded with particles like this. But the question is, from where do these particles come from? The answer to that mystery is a story that begins in 1890s. This was the time when Henry Becquerel has discovered radioactivity. Radioactivity meaning that there are actually some objects or some elements which naturally emit beta radiation or alpha radiation. Now the obvious question was, how do you compare the radioactivities of different substances? Scientists used a device called an electroscope for that purpose. An electroscope is a simple device with two leaves that are connected to a conducting rod. When you give the electroscope some charge here, that charge will be distributed to these two leaves. Now, because of the fact that same charges repel each other, these two leaves will now repel each other to some specific angle. The more the charge, more will be this angle because more will be the repulsion. Now, suppose that you brought in a radioactive material near the electroscope. Now, this radioactive material will ionize the air and particles around it. Now, when you ionize this, you create positive and negative charges. These positive charges will cancel out the negative charges that are present in the electroscope. So now that the charges have reduced, the repulsion will be reduced and the angle will also be reduced. So you take an electroscope, you take a radioactive material and you put them together, the deflection of the electroscope will slowly decrease and decrease and decrease, and it will eventually reduce to zero. More is the radioactivity, faster will the angle change. Less is the radioactivity, the rate of change of angle will be really slow. But what happened was, some scientists observed that the angle was decreasing. The angle of the electroscope was decreasing even when there was no radioactive substances present in the laboratory with them. So where was this radiation coming from? A scientist named Victor Hess chose to answer that question. So at that time, the popular hypothesis was that the radiation around us is actually coming from the rocks, the terrestrial rocks that are around us. So Victor Hess decided to test this hypothesis by going on a hot air balloon to a height of 1 kilometer. Now at this height, Victor Hess thought that the radiation here would be a fraction of the radiation that are present at the surface because we are so far away from the rocks. But he took his electroscope and found out that the radiation difference between here and surface was actually really low. He repeated his experiments at an even taller height and discovered that the radiation has now increased to multiple times the radiation at the Earth's surface. So it was clear to him now that the source of this radiation was not Earth's rocks, but is actually coming from outer space. He repeated his experiments during a solar eclipse and found out that even when the sun was half covered, the rate of radiation didn't drop. So he concluded that the source of this radiation is not the sun, but is actually coming from other celestial objects, other stars and other galaxies that are around us. This is the discovery of cosmic radiation or cosmic rays. As their name suggests, cosmic rays aren't actually rays. Most of them are highly energetic protons. Another percentage of them are actually the nuclei of atoms that are created in some of the most violent events in the entire universe. When a star goes into a supernovae mode, it actually releases a huge amount of energy. Now, some part of this energy will be released as highly energetic protons and highly energetic nuclei of other elements. After some time, they will leave the star and they will follow other magnetic fields across the universe. So for millions and millions of years, these particles will follow these tracks, follow these magnetic fields across the universe, and they will eventually reach a planet like Earth. But when this particle collides with the Earth's atmosphere, those collisions create new particles. And those particles collide again and again and again, and eventually a gigantic cascade full of different particles will form high above us. These particles include all different types of particles like pions, neutrons, protons, muons, electrons, photons, positrons, and a lot of other particles. Now, most of these particles are actually discovered using the cloud chamber itself. One such story is the discovery of positron. Positron was discovered by a scientist named Carl David Anderson. Now, Anderson was experimenting with the cloud chamber when he saw a trail. The trail looked like the trail that is usually left by electrons. But when Anderson introduced a magnetic field into the cloud chamber, the particle deflected in the opposite direction as to what an electron would have deflected. So Anderson concluded that instead of a negative charge like electron, this particle actually has a positive charge but the same mass as that of an electron. This was the discovery of positron, which is the first proof of antimatter. 4 years later, using a similar setup of a cloud chamber, he also discovered another subatomic particle, the muon. In 1936, the Nobel Prize in Physics was awarded to him for his discovery of positron. He shared the prize with Victor Hess, the man who discovered the cosmic rays in the first place. It's insane the amount of science that was discovered and inspired by the experiments that were done using cloud chamber. The thing is, you don't actually need to have a fancy cloud chamber to see these particles. You can see them if you have a bit of patience and a cup of hot tea or hot coffee or hot cocoa. In his book, For a Cup of Hot Tea, a Japanese physicist actually described seeing these trails left by particles on the steam that's coming off from the cup of a hot coffee. So to everyone else, they can look at it and say, that's a cup of hot coffee. But after watching this video, you can take a look at it and say, that's a surprisingly cheap particle detector. Thanks for watching.